Hi, it's Jason here at the Centre for Computing History, and I am pleased to introduce you to Seb Welford, an electronics engineer of the early 70s through into the 80s, who used to work on the Marconi Locus 16.
Right, yeah, that's right. I'm Seb Welford. I started my apprenticeship with Marconi's in Chelmsford, moved to EMI in Somerset for a spell, working on radar recording, returned to Marconi's, and for the rest of my time there, I worked on designing hardware circuit boards for the Locus 16.
Right. So I pronounce it Locus 16. You pronounce it Locus 16. Is there what's the right way?
We always call it the Locus 16.
Locus 16. Right. Okay. I'll try and use that one.
It's not a.
So tell me, how did you get involved in working for Marconi?
Well, as I said, I did my apprenticeship at Marconi's. It was in full electronics leading to HNC. Mm-hmm. And then I wanted to try something different, so I went down to EMI in Somerset, EMI Electronics, mm-hmm. where I designed a system which would use a commercial videotape recorder to record radar.
Right.
In my time there, I designed interfaces for many different radars, and then the call came to go back to Chelmsford. I was looking around for another job, just in case, and I had an invitation to go back, and I was interviewed by my previous boss, who the interview consisted of him telling me what had happened since I'd been away.
Right, okay. So not so much focus on it, you already knew who he was dealing with.
Yes, and obviously my CV at the time talked about using analog videotape recorders to record digital information.
Right, okay.
So I was well into digital electronics by then, mm-hmm, mm-hmm. And integrated circuits were fully available mm-hmm. by then. And so I joined the company Marconi Radar at Chelmsford in the Great Badder Research Labs. And I worked for Brian Partridge, who was instrumental in the Marconi Myriad.
Right. Mm-hmm.
And following that, they needed a small version of that, a single crate-sized computer. So he, along with Clive Gildersleeves, designed the core of the Locus 16.
Right, okay.
And I joined fairly early on in the development stage.
Uh-huh. Can you just describe what the Locus 16 was physically?
Right. It's a single, I think it's a 6U crate.
Right.
Which holds up to 20-something boards. I can't remember the exact number.
So 6U kind of.
Yes,
that kind of height.
That's right.
Right.
It's a one of the Eurocard formats.
Mm-hmm.
It uses edge connectors. A lot of the Eurocard format boards use the DIN 41612 connectors, which is in many ways a better connector. However, there's more flexibility with the edge connector method.
Right. Mm-hmm.
So it has a common backplane, which is common to all cards in the system,
right.
And there's no wiring on the backplane at all.
Right. So it's just straight through pin for pin.
Yes.
All boards connected the same.
With system controller and clock generator and things like that. Mm-hmm. And the rest of the cards basically can go more or less anywhere.
Right.
That's not always entirely true. Electronics being electronics, but that's basically the idea.
Right. Okay.
Some things didn't like being too far from other things.
Right. Okay. Is that because of speed and
it was
transmission?
Speed. It wasn't. I can't remember what the system clock speed was, but it was basically about 500,000 instruction per second machine.
Mm-hmm. Right. Okay. What was the reasoning for the machine? Why did they decide to design the Locus 16?
It was needed. People wanted to do special purpose computing for, in fact, mainly radar and military applications.
Right.
Radar was the primary thing. It got built into radars up to and including the Marconi Martello radar, which was a flat plane 3D radar.
Right.
a very early phased array radar. Well, not that early, but early enough.
And is this commercial radar or military, or is
It's
it,
a
or is it all
military
the
radar.
same? So
It's
this is all-
military,
Right.
long-range air surveillance radar.
Right. Okay. Right. Interesting. So the machine was being developed. So we've got a 6U rack.
A 6U rack.
That and the kind of electronics that's in it. I mean, it's not a microprocessor-based machine, is it? Are we talking
no.
purely TTL? No. Okay. Right. Tell us some more. Then.
Yes. The basic parameters, it was a 16-bit address, 16-bit data
Right.
machine. Later, obviously the software expanded, as it does, and the address range was extended by a paging method. But that came quite a lot later when they started running out, because you can do an awful lot with a 16-bit machine in that much memory. I think a 32K-bit memory card was one of the standards, but there were a number of different memory cards.
Right. Okay.
One thing was particular to it was that all hardware was memory addressable.
Right.
A lot of the microprocessors, there were specific hardware interfaces, and they were absolutely a pain in the neck. But making it, everything was in 7,000 hex address space, all the hardware.
Right. Okay.
So there's no worry about using specific instructions. They were just simply memory references, which made it life from a programming point of view very easy.
Straightforward. Right. Yeah.
So straightforward. Linear address space, end of problem.
Right.
So the rear connector, the edge connectors, were this common bus. The front connectors were completely specific to the function of the board.
Okay. So
Every board had a different front edge connector. Well, obviously there were common sizes of edge connector, but a different pin arrangement.
right.
And one of the downsides to that was the fact that because the handling of the cards, they had a nasty tendency to get dirty, and you had to clean them, which was a minor irritant. Mostly it was fine. Also, I had known occasions where the key in the edge connector itself fell out.
Right. Right.
Didn't usually cause any great disaster, but
Yeah.
it's called it not to work.
Yeah. So the cards are going into the rack, and there's a backplane with the where they all sit on that backplane.
Yes.
But then you're saying there's connectors at the front as well.
Yes.
And then there would be a cover or something that goes over. Does that configure the card in some way? Or?
Yes, the connector had a metal shroud,
Yeah.
and you could put cables into it. And there was also the address range in the 7,000. If there were more than one card of the same type, you could select which one it was by pin connections.
So
links.
where it sits within the memory map.
Yes,
that kind
that's
of thing.
right.
Okay.
So 7,100, 7,200s, and so on and so on.
So the cards are completely standard, and then you just configure it with whatever kind of front panel that goes over
That's
it.
right. Yes.
Okay. That makes sense.
And that had a locking screw at one end, so it didn't fall out. And the tails came out at the bottom of the shroud, and they just went off to whatever.
Right.
Some of the cards didn't have that at all. Things like the memory controllers and things like that. They may have had links, because obviously the memory cards, when you put more memory cards in, you had to tell it what address range they were.
Yeah.
But apart from that,
Right. So it's quite configurable. Then.
it was
the system.
really configurable.
And was that for a reason? Was every installation this went into different and therefore needed?
Oh yes.
Right. So this is kind of this wasn't a machine that was designed to be sort of sold and installed and just by anybody. This was configured very specifically for an application.
Yes.
In a place. Right.
Every application was different.
Right.
Every application had a different card set. But I use cards and boards interchangeably.
Yeah.
Because I've worked with so many different companies.
Right.
Call them different things.
So the technology. There's TTL logic.
It was basically TTL.
Right. Okay. And what kind of memory did it use? Was it sort of DRAM or
It
RAM?
was mostly. There was some static RAM.
Right.
It was mostly DRAM.
Right.
With onboard RAS and CAS. There was also an EEPROM board. UV erasable EEPROM board, and I remember building the eraser where you put the whole card into it, and it had 4 high power UV tubes in it. We had to make sure it had a good interlock because it could be pretty dangerous.
Yeah, don't want to be looking at it.
No. And that was programmed in situ.
Right. Okay. And what is that the main system software that was on those cards? Or was it?
Yes, it depends on the application. Main system software could live in the DRAM or it could live in the EEPROM.
Right. Okay. And was it loaded from somewhere? Was there a tape drive that it loaded from? Or
Yeah.
Right.
The load mechanism. There was a small bootstrap loader, and there were basically two load mechanisms. For development purposes, we used paper tape, 8-hole tape.
Right. Yeah.
8-hole ASCII.
Yeah.
And I got very good with the paper tape punch.
Right. Making manual modifications and that kind of thing.
Oh yes, and I had my reel of those sticky labels with all the holes in.
Yeah, join them together.
Yes. And also later on, floppy disks were used, 8-inch Memorex floppies.
Right.
That's a sort where the write protect is a stick-on tab in one corner of the disk. There were 2 sorts, I seem to remember. There was the IBM format of 8-inch and the Memorex standard, and they were completely incompatible.
Of course. They both thought they had the right idea.
Yes, but they worked. My colleagues who worked out in the desert countries, they said the desert talc tended to destroy them because you can't keep it out.
Yeah.
Because the way they worked, you could hear the discs working all the time.
Right. Yeah, and any slightest bit of dust and grit or anything.
Because I think the Marconi S600 portable radar, I think it had those in.
Right.
For signal processing. Signal processing was the primary purpose all the time.
For the machine or specifically
for the
discs?
radars?
For the radar.
Radars.
Right, okay. Right. So
I think you could do a certain amount of tracking, auto tracking and that sort of thing.
Right. Interesting.
Yes.
That's quite a lot of work for something of a relatively sort of low spec, well, for today's standards anyway.
Yes, it certainly, if you compare with what my mobile phone can do.
Exactly, so that's quite impressive to be able to get that kind of, operation out of what was relatively sort of low spec tech at the time. But, well, wasn't at the time. It was, you kind of forget that this stuff was leading edge at the time.
Oh, it was indeed, yes.
So we can only look back on it now and go relatively low spec. At the time, it was, you were looking at the leading edge.
So I suppose the competitors were probably things like the DEC PDP-8. The PDP-11 was sort of coming along, and we did actually have a PDP-11 in the lab somewhere.
Right.
I think we used it for word processing.
Well, a British company, I mean, you get it. So you can't have a PDP-11 there, or PDP-8. But so tell me more about the kind of the build of the machine itself. So we haven't had mention of a microprocessor here at all. So I'm going to assume there wasn't one.
No, the original processor, the ALP-1, was it was a bit slice.
Right.
With ROM-based microcode.
Right. Okay.
There was one particular guy whose name escapes me now. Who designed the microcode for that.
Right. Okay.
And that was all he ever did. He designed the processor.
Right. So working at the
and then he did another one, a later one. And then they started putting microprocessors in.
Right.
And I think it was probably the 8086 was probably the first.
Right. Okay.
I had a big argument with my boss, Clive Gildersleeves, because I thought the 8086 processor was horrible, and I wanted to use the 68000, the Motorola processor with its linear address space. But he was the boss.
Just had to do what he says.
So microprocessors were coming in.
So that would have been much later. That's going to be
sort of in the 70s, into the 80s.
Yeah. Right. Yeah. Okay. So the Locus 16, we've got our sort of 6U rack. That effectively is the computer. The ones I've seen though are a pretty big metal unit, sort of this tall.
Oh, so, yes.
So what else was there inside those cabinets?
Basically, the complete machine was that plus the power supply.
Of course,
and
that's
being
gonna be fairly big.
TTL was thirsty.
Right. So usually that sort of thing was like
CMOS
50 or 60 amps for the 5-volt supplies. Wasn't
Oh
it? That
yes,
kind of thing? Yeah.
yes. I seem to remember it had things like 5 volts plus 5 plus and minus 12.
Yeah. Right. So, and generally it was the 5-volt one that really
That was the
need
one.
a lot
Yes.
of current
Yes.
to drive it. Right.
Yes.
Mm-hmm. So we've got the power supply, we've got the processor rack, and then anything else in there?
One of the most useful things was the operator panel.
Right.
Because you could set in any address on that. You could set in address and data. You can read and write memory from it. You can put a stop on it.
So, what was the panel? It's not an ASCII keyboard.
It was a panel about so long with 16 address, 16 data keys.
Right. So we're talking about sort of toggle switches for
Yeah, they were those
data.
little lever switches.
Right.
Lights for every bit.
Right. So we're in the era of the blink and lights.
Yes, that's right.
So
yes.
Switches for each data bit address,
Yes.
you could say. So it's very much a debugging.
It was a diagnostic debugging tool.
Yeah.
Being able to set a stop at any address or any data access, you could set a stop on.
And its input and output would have been the control and monitoring of the radar. There was.
Yeah.
Was there a screen of any kind of?
No, there was no screen as such. That was the only screen, except that later on we had a Hewlett-Packard Logic Analyzer.
Okay, all right.
Which I designed a special board for the pod to plug into, and that was extremely useful for debugging.
All right.
Because then you could display the program, the process, the patterns that programs produced.
Right.
And then
And that was a
you could set
much
that to
easier
stop.
way to debug
Yes.
and see what was actually going on. But we're still very much working bit level on the data bus, looking at seeing what that data is.
Certainly, there was no screen as such, except in case of radar, there was the radar screen.
Right. So as a block diagram, did you you had the radar, that data fed into this system,
Yes.
and then this system then fed something out that was usable
They
information?
would feed displays.
It would feed display. So
Yes.
the kind of radar displays that we're used to with the circular
That's
thing
right,
goes
yes.
round.
Yes,
that
it'll
kind of
run
stuff.
round and round displays.
Right. Okay.
And all the computer-generated graphics for those.
Oh, so it created the output. So what it could put kind of little triangles where it thought
You put
a
up
plane would be or
the
whatever.
symbols. You put up the radar tracks were then labelled with the track number and things like that.
Right. Okay. Interesting. So that system, the Locus 16, was creating the overlay graphics, as it were, on there.
Yes.
That must be a nightmare because I'm used to a computer with a raster display. It goes down and it draws pixel by pixel.
Indeed,
on the
yes.
You're working on something that's doing 360 degrees. So that must be quite.
Well, as a programmer, because most of my programs that I wrote certainly were test programs, but I did move on to do other things because I built an emulator for the Martello radar.
Right.
And I built that using the Locus 16, and it emulated many of the things that was produced by the radar.
Right. Okay.
All the various signals.
So, but to output some kind of intelligible graphics onto something that is basically sort of a revolving, because the signal, this might be wrong, but the signal that controlled the screen to make it sweep round was actually generated by the radar itself, was it not?
Yes, there is. I can go into radar if you like.
A little bit, because I'm trying to get my head around how you
Yes.
create graphics on this screen.
Well, the bit that does the tracking and things like that tends to be fairly special purpose hardware.
Right.
Because you've got the radar scan, and you can tell the radar that the tracking machine. I'm also, in my mind, I've got a system I worked on later, which was very similar in many ways when I was at Raycal, called a Kongsberg machine, which is a similar era, and that has a special purpose hardware which actually identified where the radar returns was, and they then had a number giving its position in terms of range and bearing, and that was then converted to polar coordinates.
Right. Interesting. So so this machine was sort of overlaying the graphics that then gave the added information to anybody that was using the radar system.
Yeah.
So right, okay.
So a lot of the interfaces were communications ones. One of the first ones I worked on was an interface for it was a Yugoslav Air Force, it was still Yugoslavia in those, which I designed the whole of the interface for that. It used a particular, I won't mention where it was derived from. So it produced a serial interface, which was communicated with other parts of the system.
Right.
When I say it didn't have a screen, in fact, that's not entirely true.
Oh, right.
It would talk to a standard VT terminal.
Okay, right.
With the serial RS-232 interface.
So could that put information through one of those, right?
Yes.
Okay. So I mean, this kind of thing, you must have been under, secrecy laws and things governing what you were doing, or
Most of what I did was not of itself classified.
right? Okay. So the overall project,
the applications were classified.
Right. Okay. Yeah. So,
but it was a classified environment, certainly. But not the actual designs themselves weren't classified.
Did that make things difficult to work on because you didn't really know the end application, or was it very defined projects that you just sort of delivered on?
We tended to be given a very specific interface requirement. In the case of the major thing which I designed was an HDLC interface, high-level data link control, which is an early form of packet switched interface, and that is basically it's the predecessor to Ethernet.
Yeah. Okay. Right.
Which is now in use worldwide.
Absolutely.
It used a similar format, but Ethernet extends it.
Yeah.
Because it only had an 8-bit address field, for instance.
But then at that point, you were only talking to
That's right.
a few.
But it would then talk to a large number of other computers. And there was one particular one which never came to fruition because the government cancelled it. A multi-head radar system.
Right.
Where all computers, each heads all talk to each other on this interface.
Right.
Passing radar information back and forth and correlating the radar information.
So is that like a grand form of kind of triangulation in some way, or?
Well, yes, because if you got the information from multiple radars, then you can see the overall picture.
Okay. And how far apart were these radars? Were they,
Might have been hundreds of miles.
Right. Wow. So, I mean, at that time, how would that data have been communicated between them? I mean, was it literally cables between them?
Oh, yes.
It was, right.
Oh, it was before satellites.
Yeah.
Well, there were
direct radio links or anything like that.
Some of them were radio links. In fact, later on, I got involved in a NATO project where they were starting to look at satellite communication. That wasn't actually using Locus 16 itself, but it was all allied. And we had to look at the telephone system as well, and because digital telephones was starting.
Right.
We had to work within the parameters of that. And that proved quite tricky.
I should think so. I mean, so that would be just using the cabling that was there, or was it actually using like the BT exchange to get data
It did
through?
use BT. It was all encrypted. It was encrypted at source.
Right. Okay.
So it then used the standard BT links, including satellites.
Right.
When satellites were actually proving to be quite a serious problem
Really?
because of the way that links work. Because it worked on a ring of 8 messages, and each one had to be acknowledged. And if they weren't acknowledged after 7, you started again. And the transit time for the satellite and back was a problem.
Too long. Right.
Yes, and they were still arguing about what to do about it when I left.
Right.
So I don't know what actually happened to that project. I won't mention its name because that probably is classified.
Right. Fair enough. I won't be sure. So back to the Locus 16. Do you know how many of these systems were out there in use?
I don't.
Are we talking tens or hundreds, or?
I would think hundreds.
Right. Was it? Obviously, it wasn't specifically British. You were doing these for other countries as well.
Mainly British.
Right.
I don't know how many, because quite a lot of them when the S600 radar, which had them in, when you went out all over the world, including to the Falklands.
Did you have anything that the Falklands sort of impacted on your day-to-day work, or?
Funnily enough, it did later.
Right, later. So right, okay. Anything we can talk about, or shall I move on?
No, that's of itself unclassified.
Right.
Because when I left the company, I went to work for Racal, who used this Kongsberg machine, which is similar in generation to the Locus 16.
Right.
It's a 16-bit machine. It has some rather peculiar characteristics. But one of the biggest systems installations of that was the RFA Argus, which was used in the Falklands, was hired by the Navy as a contender Besant, and converted into a helicopter carrier with a five console command system.
Right. Wow. So you weren't just designing the boards for the Locus 16, you were also getting involved in the programming side.
Yes.
How did that come about? I mean, you started with the electronics.
Yes.
I find this interesting because kind of that's where I got later with microelectronics and microprocessors and things.
Right, yes.
But I started with the hardware and ended up falling over onto the software side because I designed the hardware.
Right.
It made sense to get involved in and write the low-level code that pulls it all together. How did you end up working on the software side of things?
Well, the HDLC processor, which I designed, it was a two-part. It was a DMA direct memory access controller, which was used for the HDL processor and also for a drum store, which was designed by somebody else. And they did a fairly high-speed, large-capacity drum store. And those were micro-coded, hard-coded bit by bit in PROM. And I think it must have been a 64-bit wide microcode, which controlling the HDL1. Right. So that was software, if you like, but it's software in hard PROM.
Yeah.
No assemblers or anything like that.
Yeah.
They were just talking about microcode assemblers when I finished that project.
Right.
That seems to happen to me.
You do the hard work and then somebody comes along and
Yes.
creates an easier way of doing it.
'Cause-
That's tech in general, I think.
Because following on for that processor, it actually worked extremely well. It also had to work in a high noise environment. So I took it out to the Rivenhall airfield, where there were many large radars, and had it spanning across the airfield, and it ran for a week without a single error.
Right.
So my design of the interface for that was very successful.
Stood up, right, yeah.
And that was running my software, because I designed the processor, and all the processors had test programs, mostly written by somebody from the software department. But then there was no way to do it. So I said, right, I'd better get on and do it. So I had to write the test software in a very rather peculiar way.
Right.
And it just ran through and produced the reports. Cycle 1, fault 0. Cycle 1,000, fault 0.
Right.
And you just left it running.
Yeah. In a loop and just sort of...
And it just sat there and just did it.
Right. And stopped when it found an error or gave some sort of report if it
Yes,
did find it?
it told you
Or you just assumed if it was still running, then it was okay?
If it was still running, but it had specific fault codes.
Right. So were you testing the microcode you'd done, or was this the microcode itself?
That was the microcode itself. Obviously, that controlled the function of the processor, the interface processor itself.
Yeah.
And we then had to test the function of that in a test environment,
Right.
because it was a bidirectional processor with a 1 megabit per second interface. And it was a bidirectional, so you could loop it back on itself.
Okay, it's not a term I've heard before. Bidirectional processor.
No, processor.
Right.
All right.
Okay.
It's an interface.
Right. Yeah. I'm sorry. I'm with you.
Yeah.
Right. I thought I had a new type of processor.
Transmit and receive.
Yeah.
You could do them at the same time.
Yeah. So it's full duplex. Kind
Yes, that's right.
Right. Yeah.
That's a good term. Duplex.
Right.
Yes.
Okay. I'm with you. So the code you were writing probably had to go through quite a lot of checks and double checks for its installation, or was that not the case?
Yes and no, because
Right.
I actually ended up as the software quality manager.
Is that a good idea?
No.
It would be a good idea if I was doing
It was very bad.
right. You tend to assume that you've got it right.
Like the thing I was about to tell you, I probably won't tell you now until I've got the camera switched off.
Fair enough. Okay.
But because that possibly is.
Okay. Yeah. We'll gloss over that. But the having this the software and you go to the lengths of literally taking them out to a high interference place,
Yes.
like airfield,
Yes.
and make sure it could hold its own
Yes.
in amongst all this. And we're talking about electrical noise generated by these other systems, or are we talking about
big radars,
Right.
multi-kilowatt radars.
right?
I think the worst was a height finder.
Mm-hmm.
There was a Marconi height finder which stood about 20, 30 meters tall,
Right.
as a single dish, and for the surveillance radars told it where it wanted the height of a particular target, and you told it where it was, and it swiveled round and nodded once, and
that would give you the height.
and that was I don't know what power it was, but it was multi-kilowatts.
Yeah. Wow. So you're talking about sort of well, there's just about every type of interference there, isn't there? You've got RF
yes.
and electrical sort of.
There's mains-borne noise.
Yeah. So the whole system was heavily guarded
Yes,
against all that kind of.
volts per meter were off the scale.
Right. Wow. So that means that the communication system had to be tolerant to that as well.
Yes.
So things like RS-232 isn't any good in that kind of situation.
422, which is balanced.
Right, current loop kind of
Yes.
set up.
And this was if you like it used. I think actually one option was to use RS-422 chips to do the interface, and the other one was an interface which I designed,
Right.
which was a rather higher level, higher noise immunity.
So this is quite a clever system, really. I mean, for those people that don't know, you've got for your one signal you have two wires, and you've got the positive and the negative transmitted opposite on each
Yes,
one,
yeah.
and any noise picked up affected them both,
Equally.
therefore cancelling out. Yeah, equally.
Yes.
Therefore cancelling out that noise.
Yes.
That's a kind of a stroke of genius. In my
As
book.
long as the receiver can cope with the noise difference.
Right. So it
The
could go
receiver
outside
can
of-
cope because they go up and down together. But if
Yep.
it goes outside, if the noise level exceeds that, and it will still break down.
Right. Is that physical damage to the receiver end, or is it just can't cope with it
Only
and
in extreme
decodes?
cases.
Right. Yeah. I should imagine you might be near those extreme cases in this kind of situation. But okay, so I mean that's quite interesting to be developing computing technology for those kind of environments. With the sheer amount of outside influences that are going to knock your system over, potentially knock your system over. Is there extra code written in the software to check and double check, or was this all handled by the electronics and
Mostly,
made sure?
basically by the electronics. One
Right.
thing we had, there was a big worry at the time, and I think that worry seems to have gone away, I'm not quite sure, was memory corruption due to cosmic rays.
Right. Okay.
And at the time, we used parity on the memory. And I can't remember whether some of the boards used double bit parity, because single bit parity you got error detection, but
Yeah.
double bit you can have error correction.
as well.
There was also the Hamming code, and the other system I worked on that had Hamming code chips on the memory boards.
Right.
So they were pretty much immune. But interestingly, from an electronics point of view, the cosmic ray flipping of the odd bits seems not to matter. Because I think most PC memory cards nowadays are non-parity,
Yeah. Parity.
which
seems
rather
to-
surprised me when it started to happen. Because the early ones I did were parity.
Yeah. Parity was on a lot. Well, I think it's still on sort of certain server memory and things like that. But
Yeah.
I suppose to the end user, if it crashes, nobody really knows why they turn it off. They turn it on again. Standard IT support.
Yes,
kind of stuff.
yes.
But so is there anything else about the Locus 16 that?
There were a fair number of different interfaces, RS-232. There was parallel for paper tape punch. I think the SDP-1 probably had a parallel interface. Obviously, there was a floppy disk controller, which we had there were 4 floppy disk drives, and when they were going, they made a very clack, 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 clack sort of noise.
So these are the 8-inch drives.
That's right. Yes.
And what sort of interfaces are these? Again, are these TTL based, or are they starting to use specialist?
They were proprietary interfaces.
Right. So you did the work of interfacing those.
Yes,
proprietary
that
chipsets
wasn't
to-
me. That wasn't my bit. Somebody else did
Yeah,
those.
yeah.
I did mostly the external comms interfaces.
Right.
I worked on quite a lot of those. It was a RISC machine, if you like.
Okay. Reduced instruction set.
Yes.
So,
And which made it a very nice machine to program. I've programmed a whole load of microprocessors, and nothing comes close to
Right.
the Locus 16
interesting.
in niceness of programming. One particularly good thing about it was the way it handled a stack. All the microprocessors I've come across have all been push and pop,
Yep.
which is extremely inefficient.
Okay.
Because that's an instruction cycle per push, an instruction cycle per pop, and if you've got a lot of data to pass on, that's quite a lot of instruction cycles. But with the Locus 16, the stack register was a T register, and in the assembler code, you just said add T space literal, and you just claimed as much stack space as you wanted on entry. You then use stack space, and you could just do sub T space literal on the way back out again.
Okay.
And so that was only one pair of
much more
instruction cycles per stack operation, which made it fully re-entrant. It was such a nice machine to program. I've programmed a whole load of other machines. 8086s, 88000s, 68000s, 6502s, you name it, I've programmed it,
Right.
but nothing comes close.
Yeah. So do you think there's a reason why that way of doing it hasn't been re-implemented anywhere else further down the line?
I think, but the push and pop mechanism had been so ingrained by the Americans.
Right. Right.
Intel in the first place, probably with the 4040, and then the 8080 and the 8086.
Yeah. Maybe that's something for somebody looking at the next generation of processors to go back and look at history and.
I would love to see you program, but nowadays it's all mostly done in things like C++ and Java and what have you.
Oh, well, people are so far removed from the processor, it's,
Yes.
you don't really get to look at it. But we still need another generation of people that know that low-level coding and
Yes.
understand the microprocessor to that extent.
Because
they
if
can
you
create
want
the next generation.
if it's embedded hardware, embedded processors in hardware, you still actually need to be able to use assembler, to my mind. Because if you want it really efficient, because a code compilers produce is pretty good nowadays.
Yeah,
but it's
it's a
still
lot
you
better
can
than it used to
still
be.
do tighter code
Yes.
with assembler.
Yeah. Yeah. No, that's the trade-off with anything like that.
And there was a compiled language was Coral 66.
Okay, heard of that. Yeah.
And that was the ministry standard, MOD required standard language.
Right.
And there was a cross assembler and a cross compiler on the Marconi Myriad, which is another very interesting machine. It's a 24-bit machine, comes in the desktop. So that was that was a bureau machine.
Right. Okay.
So you sent a tape off overnight,
Yeah.
and you came back
Process it
with
for
the
you.
error printout. So you do it again.
Yeah.
Edit the tape. And then there was somebody produced a native compiler for the Locus 16. There was a native Coral 66 compiler.
Right.
So that made life much easier.
So why did the military sort of favour Coral 66?
It was early days for high-level languages. I don't think the only thing prior to that was Algol. It's a commercial language. And Fortran, which again it's a mathematical language, it's not a procedural language.
Right. Right. So
Was
Coral 66 developed by people relating to the MOD, or was it?
I'm not quite sure.
I'll have a look at that.
It was around. Various companies produced cross compilers for all sorts of things. I'm trying to think. Logica, I think they produced cross compilers. We actually ended up with a cross compiler for the 8086.
Right. For Coral 66?
Yes.
Yeah, well, these languages do tend to live on a long time past
Yes, basically.
the time where people think they should have been dropped.
Yes, but Coral 66 was then, of course, succeeded by Ada in the military world.
Right.
And Ada is a lovely language. I would very much like to use it now.
Right.
It takes a bit of getting into.
Yeah.
It's quite tough. But once you got into it, you think, why would anybody want to do anything else?
I think the same with Perl, but then there's going to be about 1 million people online laughing at me now. But anyway, so it was working with Coral 66. You had the cross compiler there. Did you do any work in Coral 66, or
I did lots.
Right, okay.
Yes.
So language you become very familiar with.
Yes.
Right. So okay.
And then I started using C. And I got a C compiler for the PC. No, the first C compiler I had was with the Z80 add-on for the BBC B.
Ah, right. Yep.
And that's where I really got into C.
All right. That's more my generation now. So.
And so Coral, some programs I'd written in Coral, I actually recoded that in C.
Was that a big task, or
not enormous?
So is there anything you can tell us about the Epogen system?
Very little, I'm afraid, because I knew that it existed,
Right.
but because it was a Leicester project,
Right.
it was not ours.
Right. Okay.
And I think it probably is fairly high level of classification on that.
Yeah. But that was based on Locus 16.
Well, that was the core processor. Then there was a lot of specific hardware
Right.
for the picture generation side of it.
Right. Because that was the system used for Seawolf trainer aimer system. Right. Okay. So.
Yes, some of my colleagues were involved in the Seawolf missile Seawolf tracker.
Right. Okay. Interesting stuff. Well, thank you very much for your time. Really appreciate you telling us about the Locus 16.
I'm glad to sort of be able to pass on what knowledge I have.
It's important that we do get this information. These are a whole range of machines that were doing incredibly important.
It was a generation of machines. It's the early generation of small computers. Computers you could actually pick up and carry.
Yeah.
The previous ones which came on the back of a lorry. Going back as far as Leo, of course.
Absolutely, yeah. I mean, it's strange, isn't it, how in sort of one working lifetime we've gone from those kind of machines, from those big ones that did need to be on forklifts and moved around like that, to ones you could just about pick up, to machines now that are in your pocket, they're infinitely more powerful than they ever were.
Well, the phone that's in my pocket is ridiculously powerful.
Yeah. And that's just easily in a working lifetime, and it's just
yes,
incredible.
In my lifetime, I've gone from paper tape through memory sticks, USBs.
To holding the world of information in your hand.
Yeah.
Just at such a bum. Incredible. Well, thank you very much for your time. Really appreciate it.
Not at all.
We really appreciate you taking the time.